Hi, I'm Paul Teich, Materials Research Principal Analyst, and welcome to Wednesday morning at DAC. I'm a 35-ish year industry veteran on the hardware and software side, and wanted to get a quick poll from you people who've showed up early from the keynote. How many of you think Moore's Law is dead? Raise your hands. Moore's Law is dead. Moore's Law is alive, healthy and kicking. Moore's Law is in a zombie-like kind of quasi-dead state. Okay, anybody in the middle? Slowing down, okay. So integration, I think, used to be a driver for increasing the functionality of a piece of silicon. We're gonna see as I go through my talk that increasingly it's being used to incorporate more features of an entire system, entire hardware system, at a local level, and a lot of compensation being given to whether Moore's Law is alive or dead in the design decisions being made in the industry. Let me get the right direction. So we used to think of system on chip. I worked at AMD for 20 years, and so our goal was a bootable system on a chip, and to do that, we actually wanted to integrate everything onto the same die. And CMOS, current state of process, whatever it was. To do that, you have to control all of the intellectual property that goes on the die. You have to license it, you have to natively invent it, and what we're starting to see is that the intellectual property arena is becoming complicated enough, and the processes needed to produce optimal memory, or optimal radios, or optimal logic are becoming different enough that we're moving to a situation where we might have thought of putting it on one die, say 5 or 10 years ago. Software-defined radio is a big one. I want to put that on my current state-of-the-art CMOS process, and that really isn't something we talk a lot about today. So we're starting to move to system and package technologies. The key to same die integration, basically we get Moore's Law gives us density. Okay, that part of Moore's Law is not broken. We get twice the density every time we make a major process transition, but that comes at a cost now with leakage current, and we're getting to a state of leakage current where we're actually not sure a lot of the time, as we get to 5 nanometer especially, that the result of a computation is actually valid. Okay, there are not enough electrons going through the gate in many situations to be absolutely sure that we made the compute. So we're actually doubling up on the logic to make sure that the event that we thought we were measuring actually happened, and that actually decreases the area that we have available. So although we get the additional density, we're not actually sure we can use the additional density much under 10 nanometers at this state of development. So multi-chip packaging gets us around some of those problems in that we can use the most cost-effective die, the most manufacturable die, or the fastest, most performant die for any given function. So on one side, access to intellectual property is important. On the other side, and that's system on chip, integrating everything onto the same actual die. And for multi-chip packaging, what's important then is partnerships and the packaging technology. And what we're seeing is a lot of innovation on the packaging front and a lot of folks drawing partnerships so that they have access to somebody else's state-of-the-art known good die. So where do you draw the line? What do you integrate? And what we're finding out is there are no hard and fast rules. I think radio was the first dream software-defined radio of integration onto CMOS that has kind of been dropped. It's much more efficient to do radio in 48 or 60 nanometer technology than it is to try and shrink radios down below 20 nanometers. It's just more cost effective, and software-defined, what we've practically found is the number of transistors that you need, logic transistors that you need to do a software-defined radio is a lot, and it outweighs the older, more established, more stable analog radio technology. The trade-off becomes, I just want a radio that works doesn't need to be that flexible, and I'm going to hit a particular design point with it. So we have customers who do IoT endpoints. I say secure IoT endpoint only to drive home the point that no IoT endpoint should not be secure in the future. Okay, we can have a whole hour discussion on the benefits of doing security in IoT. But at an IoT level, your choice of radio, your choice of memory, both volatile and non-volatile, the choice of processor and analytics acceleration are also highly variable in product generation to product generation, that trying to integrate everything onto one die every time you turn the crank on doing a system design is actually kind of a losing proposition in terms of design engineering resources. All the way up to servers, to folks doing, at this point, 64-core servers, and much farther beyond that. You'll start to see in the next year or two. And there, the idea of a bootable socket turns into an exercise in, okay, so I have this huge die because I've got all of these cores. I'm going to put a lot of uncore with that. I've got memory controllers. I've got all my PCI Express breakouts. I've got my interface to my boot logic, power management interfaces. How do I put all of that into a system design, and what do I not put on it? I mean, do I actually put USB interfaces on my server design? All of that those are design points that each server processor manufacturer is taking a different stand on. Okay, and that kind of starts looking like this. So this is NVIDIA's SMX2 module. This is the P100, the Pascal generation. They've just announced their Volta generation. This is a multi-chip package. So this is a very large GPU die, and faintly on each side of it, you can see 4 high bandwidth memory stacks, okay, with some filler in between there for thermal coupling. And this is 300 watts of voltage regulation on this side of this. So this is a 300 watt chip solution. It's actually a very nice mechanical package because all of this is planar, so you can put a flat planar cold plate on top of it and then do a big air cooling stack or some water cooling on top of it. But very sophisticated packaging. On the Volta generation that they just announced, they actually have inert silicon die fillers. They used a different filler on the Pascal generation in order to get the thermal characteristics to be the same, because this is a very hot chip and they want the expansion characteristics to be pretty close to identical across the surface of the chip. So in this design, NVIDIA went with a monolithic processor. And this is actually a coprocessor. So all of the other logic in the system, this only has PCI Express and power interfaces and NVIDIA's NVLink. But all the rest of the system design stuff is actually in the rest of the system design. This is AMD's newly announced. At the time I did this presentation, AMD EPYC hadn't been announced. There weren't a lot of details. They gave that over the last 2 days. It is a 4-chip 4-processor chip module. And the way AMD decided to break it out, other than the discretes on the board, is that each of those chips has 8 cores. And they can scale this up or down. 1-chip solution actually turns out to be their desktop processor. Okay, 2 chips, they've got, anybody here heard of Threadripper? And a 4-chip is their server processor. So the idea with AMD's EPYC is that each of these chips has 2 memory controllers on it. So the aggregate is there are 8 memory controllers in this system design. Each of these chips has a system interface that's got USB and some other functions on it. And so this is a complete bootable socket where each of the chips has a portion of the overall functionality evenly split up. They only use one of the chip's system management blocks to manage the whole complex as the external interface, but they all have it. So it's identical die across the design. Now this is one way of kind of splitting up the functionality so you don't have a huge monolithic die that's hard to manufacture, has high defect densities, and is very expensive. And then we get to the Internet of Things. And so in the IoT, what we're seeing is vendors are splitting up their integration based on functionality. So we have here is a couple of Motorola modules where the substrate is a piece of fiberglass now and moving toward kind of printable materials. And they have DRAM, they've got a ROM, they've got a processor and a DSP and radio chips, all integrated into a single package, okay? And what makes this appealing is the fact that they can decide farther along in their design cycle to change part of this, to put a different radio in. And it becomes a package layout problem and not a, I need 2 more years to go spend a different piece of silicon problem. So this, again, this planar, this is on fiberglass. This is on a manufactured, not quite fiberglass substrate. And these package up very small. These are only about 3 centimeters on a side. So very reasonable sized packages, very easy to integrate in with an endpoint device. And also kind of cool. So I think one of the biggest attributes here is that you can supply just enough power to each of these parts. They can be power managed separately, okay? So that helps reduce the power in the system because you don't have to power one die to do everything it needs to do and then individually get blocks on the die. And so power management on a monolithic chip is a different question than actually running each of these die at an optimal speed and dividing up the interfaces between the chips very nicely. So we've seen some people do wire bonding. I've got more pictures of this, but essentially you can stack die and use a very old technology like wire bonding to connect these stacked die together and have a very small volume of space that's got antennas and sensors and radios and compute power all built into a very, very small package. This also, at manufacturing time, you can decide you want a different supplier for a DSP. And as long as it kind of fits this general form factor and you're not generating too much heat, this kind of packaging works quite well. We see a lot of it, if you're familiar with Arduino and IoT experiments and putting shields on top of a standard processor, they're great development environments, but they're really bulky and cumbersome to actually ship into an IoT deployment. They're also not very reliable because the parts will shake apart very quickly. And what we see is people experimenting with these stacks of Arduino shields, and then once they get the right functionality down, once they do their software prototyping and get the application solid, they push it down, and this is 2 halves of the same planar here, into a very tightly integrated board-level solution. Here's an ARM version of this is a solar harvester on top of a board that's got a radio and temperature and humidity sensors on it. And so this would be deployed out into a field in an agricultural kind of environment. And the important part here is best of breed chips. So you've got a radio, you've got a power supply, you've got a processor, and you can pick what your application needs very close to manufacturing time. I'll go back to, there isn't an end in sight to shrinking these devices for IoT because the packaging is going to get more innovative, okay? So as we look at where the innovation is going, I don't think it's going as much toward integrating onto a system-on-chip design as it is toward packaging these individual chips, venting the heat, and making sure that you get a clean radio signal out of it. This part right here, that's my thumb, by the way. That's 1 millimeter by 1 millimeter by 2 millimeters. Okay, very, very small package for kind of an IoT mote to do some remote sensing. So, but that's not my product. So everybody who's designing for the IoT and doing this system level integration has to remember that The I in IoT means your product is not standalone. Okay, when you're making decisions on what to put in your product, you've got some local decisions you need to make on how fast you need to make decisions and with what kind of local sensor input. And you've got this whole cloud thing behind you that provides much deeper context. And your competitive arena is that everybody's going back to the cloud to do data ingress, collection, analytics, and draw some kind of higher level conclusion about the data you're gathering from your IoT sensor. And so, we're using the consumer example here, Amazon Alexa and Google Home, where we used to be able to turn our lights on and off. How many people are old enough to remember the whole clap twice thing, your lights turn off? Okay, we've gone way beyond that now. In fact, if you have an Amazon Fire TV, you can light up Alexa on your Fire TV. So it's an app, doesn't actually need this dedicated device. But the key here for consumers is natural language processing. In the industrial Internet of Things, there are other concerns, but I'm using this as an example because it's kind of easy to highlight what's going on here. Intelligent devices need some kind of really aggressive processing to do natural language understanding. And so if you do it in the cloud, you can use these massive processors. So today, FPGAs, general purpose graphics processing units, the GPUs, and custom silicon are being used to interpret your speech remotely and for the bulk of the complex commands that you do, and then being pushed back down locally, and there's a latency equation there that has to happen. I'll just point out, this is obviously a GPU. That is an FPGA card, and the board on the other side there is Google's new TensorFlow processing unit, 2nd generation. And so if you're using Google Home, there's a data center full of those TPU2s that's actually doing the speech recognition beyond everything other than the hello Google or whatever your phrase is that it recognizes locally. So services and infrastructure. The IoT, no matter what you're doing, industrial or consumer, is an infrastructure service. And it really meets the road in this gateway architecture. So at some point, you have a sensor. It's acoustic sensor, it's temperature, humidity, it's vibration, it's detecting gases, carbon monoxide, carbon dioxide, whatever you're looking for. But that has to go back to the cloud, and it's our observation in the industry that not every device needs to have an IP address, and not every device needs to have a cellular radio in it, okay? There's a midpoint at which the cost of the endpoint, multiple endpoints, is outweighed by the fact that you can have a gateway in your house. It might take the place of your Wi-Fi router that does data collection and has some intelligence in it to do local processing off of the actual endpoint device. And why that's important is because the closer you get to the cloud, the more context you have. The closer you get to the cloud, the more intelligent insights you can get from data from 5 million people just like you, if it's a home device, or from a factory full of robotic automation learning about the task of building a car or building construction equipment or whatever it happens to be doing. So that learning increases toward the cloud. Latency decreases as you go locally. So pushing intelligence to the edge is generally good, but it's a cost and power and space trade-off as to how much intelligence you can push to the edge. So each IoT design is a balance now. It's not just the local system, it's a balance of what do I want to accomplish in the local system, but what is my overall context for the task I'm trying to serve, whether it's even just delivering recipes to somebody at home. So you start with your sensors. A lot of people think that humans are like the apex in the natural world of sensory input. We have the best eyes, the best smell. That's all not true. But certainly we can do much better with machines. Okay, so we're deploying sensors that have better than human senses. And where that comes out is in I'll use a simple application as an example. Alexa has to be able to hear you across a room where a lot of noise is happening. Because you're actually using your Fire TV or your Google TV or whatever. You've got different house members talking to each other, got noises from outside. And you have to do something called far field voice recognition. And so at the local level, they have to put a lot of processing together, a lot of microphones together, to actually enable the system to intelligibly hear a specific voice giving a specific command. And so their OEM development kit is 7 microphones and some fairly aggressive DSP. It's got an ARM Cortex-M series processor in it. And it's doing a lot of work at a local level, just listening for the key phrase, Alexa, to come from somebody who it's supposed to respond to. But if I want to build some of this from scratch, what do I need to do? This is actually a workbench here for a company in town called Unaliware, and they're building a tracker, but it's not a tracker for most of us. It's a tracker for seniors who have some cognitive impairment, and so they like to say it's OnStar for seniors. Okay, and so this watch here is a sensor platform. Okay, it's got accelerometers, it's got timers, it's got all sorts of stuff in it. It has voice recognition, it's got a touch interface. It's multimodal because you can't count on somebody having steady hands, you can't count on somebody being able to hear well. So they're trying to provide as many modes of interaction with the wearer as possible. But once you build the hardware platform, and by the way, I'm wearing a Garmin right now, so I'll generalize to that platform's accelerometers are not the same as the accelerometers in the Garmin I'm wearing. So once they put their platform together, how do they determine that someone's taken a step? How do they determine that somebody's fallen asleep? How do they determine that I've walked out of my geozone, because that has GPS in it, and it's designed to make sure that your grandparent or your parent doesn't unintentionally walk away from the house and you don't know it. And so what they have to do as they're designing this product is they have to do extensive alpha and beta testing on a lot of users, because designing the sensor platform is only the first part of designing the service that's based around this IoT platform. Okay, so they're going to go through perhaps a year of people wearing this hardware platform before they can actually start to deploy it, because they have a lot of data analytics in front of them on what is a fall. Okay, what happens when somebody falls, they can't get up? What does the accelerometer profile look like? Okay, what is the rest of the sensor package saying at the time? If somebody's fallen and they're unconscious, they can't speak to it, they can't touch it. And so to build a reliable product that provides a high level of quality service, they have a lot of data analytics in front of them, even though they've already built a hardware platform. It's manufacturable, they can have it built in volume and ship in volume, but it is useless without that cognitive service behind it to figure out what that data is telling them. So as you're designing your service, you have the product that you sell into an industry or an individual, and you've got a data center behind it. And increasingly in the middle between those is a gateway architecture. For consumers, it's probably a Wi-Fi gateway, but in an industrial space, it's going to be not just a protocol gateway, but some kind of intelligent data aggregation point that then lets you offload some of the work from your IoT endpoint to lighten the load there, both on power consumption and on cost, and act as an intermediary to the cloud, which has all the wall power you can need. You probably need to buy a power substation to operate it. And these things are in the megawatt range now, but gives you the intelligence and the context you need to operate a state-of-the-art service today. So with that, Oscar, if there are any questions.
So in the keynote this morning as well, he was talking about some of these features and whatnot. What's your perspective on where the value proposition is here? I understand why companies want all this data and want to process it, and there's some interesting use cases where there's value add to the people, like the example you just, the consumer. The example you just gave is a great example. But it seems like what's the weighting? It seems like the value proposition to the consumer is a lot lower than the value proposition to the companies collecting all the data.
Great question. A lot of it has to do with the company's privacy policy and intent. Okay, so if we take social media out of it and we stick with the Garmin's and Fitbits and wearable technology, I own several pieces of hearable technology, that help filter ambient noises and things like that. And in one respect, those companies need data to refine their service over time. Part of the promise of these products is that as you get more wearers, as you get more users, the product becomes better. Okay, there's actually I have a pair of Doppler Labs Here Ones, and they now have a BART filter for any of you who live in the Bay Area or travel out there. There's a specific filter for a very noisy subway system, Bay Area Rapid Transit. Okay, and so, but that wasn't shipped with the product. Okay, they have enough people in the San Francisco, Silicon Valley area who take BART who are complaining about it that they actually gathered the data from BART remotely from these products and built a BART filter. Okay, that is a benefit to the user. Okay, and you'll find as these speech recognition systems become better, they'll become less intrusive. My wife's phone pops up every once in a while. It's an Android phone. And Google says, "I'm sorry, I didn't understand what you said. We didn't ask it anything." That's just randomly popping up during conversation in the house. Are you listening to us? And so that hopefully gets better. And so we make trade-offs as consumers as to what we want. In a factory setting, the factory owner may consider the data that the sensor's gathering to be proprietary. And in fact, this is actually a problem for some industrial IoT settings where the manufacturer can't have access to the data once the IoT endpoints are deployed. So that generation of product gets deployed. It doesn't improve unless the customer shares some representative data with the manufacturer of the endpoint. Okay, so that's a trade-off that the manufacturers make, that they may or may not be able to share representative data. Maybe a trade secret, it may be a government secret, maybe military, some kind of military development. But that again is an explicit trade-off in the deployment. Did that answer your question?
Yeah, it did. With regard to that last point, do you see companies giving, or I guess it'll be interesting to watch and see, if consumers demand it, not in an industrial space, but in a consumer space, the ability to turn it off,
right? To turn what part of it off?
The feedback. I mean,
sure, yeah.
Right, like with a hardware switch, so I know somebody can't come in and hack the thing over and override it.
And I could see that happening. That's more of a programming verification thing. I know in some countries they require that the wall warts to recharge your phone have an on-off switch, so that you can explicitly say, I want to keep it plugged in, but I'm going to switch it off so it doesn't consume any power while I'm not actually recharging things. Those are going to get smarter, but it's the same kind of functionality, right? Yeah. Any other questions?
Yeah, I mean, one example of this is the driving app called Waze that, social media, it figures out where there's traffic is moving more quickly and tells everyone else, hey, to take the 35 instead of, the main street to get around. And then you get the reverse where people have their shortcuts, and then, people who also know the shortcuts say, turn off Waze if you take the shortcut by my house, because it's okay with you being here, but I don't want, all the rest of the world. And some, you mentioned California, there's some towns, Los Gatos now closes their entrance to the 17 freeway on the weekends because Waze was taking everybody through the sleepy little town because it's 2 minutes faster than staying on the freeway.
Right.
So you get these
Yes.
unintended kind of complete change. I mean, the town never cared about any of that stuff. Now suddenly they're putting up a roadblock because of this freaking IoT.
So, and that's a good point. That's I'll actually add that to my next presentation. The law of unintended consequences multiplies when you have a complex system of systems. So it's kind of, there's a study of cellular automata, okay, where you have simple behavior like ants, okay? Each ant has a very simple set of behaviors. But when you combine the behaviors, you get a hive behavior of the whole ant nest, which is a more sophisticated behavior than each individual displays. When you combine a bunch of IoT sensors with a bunch of analytics, the analytics may be able to pull unintended patterns out of the data, okay? So this thing tracks my sleep, tracks my motion. I like the fact that it does that. I have no idea. I'm a coffee snob, and I own a hand coffee grinder. I don't know what it makes of that. Okay, I don't know how that shows up on the accelerometer. Somebody's got to be looking at that going, looking for other people who have that pattern. And eventually they may tie it back to, oh, he's a coffee snob, he's got a grinder. Okay, and that's the motion, right? Swimming, whatever sport I'm doing. People who wear this 24 hours a day, eventually they're gonna know a lot about your personal habits. Okay, as more people wear them, as they're able to tie, I'm eating dinner, it's this time, I travel a lot, so whatever time zone I'm in, what am I doing, okay? Walking is easy, but more sophisticated behaviors, they are gonna be able to pin, and they have a heart rate sensor in this now. Okay, so not only do they have my motion, but they have my heart rate, and they can correlate those for different kinds of activities. So it is going to get a little bit more scary in terms of the data we can put together.
Yeah. You got a question? Well, I mean, the other one that the gentleman in front was asking a question about, hey, I want to turn it off, or I want to. I mean, one imagination is you would have a digital persona that is my ID. So it could be like my Facebook account. Well, I want to have two Facebook accounts. One is I see all my family and the kids and what's going on, and this other Facebook account, sharing with people at work. Maybe a third one, I'm playing online games. I don't want my boss to know that I play World of Warcraft, right? But Facebook wants everybody to know everything about everything.
Oh, and Facebook actually will be able to tie those. You violated their EULA right there.
Yes,
right?
absolutely.
But
can we take that back and say, look, I want to have a digital ID that's me, that I actually own all the data about the fact that I make coffee twice a day, or the fact that I drive this way. They talk about with the airplanes, airplane
Right.
Bill of Rights, passengers, we want to have big enough seats or what have you. Can we, the people, have some impact into this IoT and say, look, I own that data. You can use it to make my life better, but I want to have a switch, a guard, something around that.
And I think Europe is far ahead of other geographies there right now in terms of personal privacy protection. That's something that has to be legislated, okay? Because the manufacturers are going to gather that data to improve their service, and unintentionally they're going to know a lot about you. That turns out to be monetizable data, and so what do you do? That's a business decision, right? So yeah, I think are we out of time? Think we're good? We're starting to increase the time. So all right, great. All right, thank you very much. Very much appreciate your time here.